go time. Drives me nuts how many screen calculator copying bums there are in this world. And because you've touched that fraction button on your calculator for so long, you can't do what Lexi Samuelis has already learned to do as a 9-year-old. Boom shakalaka. No faces over there. All right? Okay, sorry, you can't see? All right, so there's the intro. So we're going into the world of probability, which probability is going to be fractions. And it makes me so sad how many students these days can't deal with fractions. So offline, I picked the students. We're going to answer these questions without a calculator. If I see a calculator, I'm going to karate chop it right out of your hand. You got it? All right, here we go. Resume. I almost hit stop. That would have been a disaster. Okay, so we've gotten through 2, getting common denominators when we're adding. And then, and then 1 becomes 24 over 24. And then this you could write as 1 and what's left over? 13 24ths, right? That's writing it as a mixed number. The previous one's called an improper fraction. Okay, now we're going to get into these, and then I don't know how much more we'll do, but I enjoy this. I really do. All right, resume real quick. I don't know how long I'm going to bother these students with these little things, but these little basic things. When you add fractions, you get a common denominator. When you multiply, you just multiply across, but you are allowed to cross-cancel to reduce the fraction ahead of time. Division is multiplied by the reciprocal. I don't think I want to go over these too much. It's not really a big deal. I feel like it's a waste of time. Okay, but I would like you to think fractionally, know these basic ideas for fractions. It makes me infinitely sad how many seniors I've seen throughout the years that cannot deal with fractions. All right, and that's why, kind of covering that. All right, you write what you want. I like to give the book props. I like to tell you that you don't need me. And in college, you will have to read a book anyway. 90% of what you're going to have to learn in college, you're going to have to do it yourself. All right, the instructors sometimes will say, read pages 1 through 30 before you come into my class next time, and you have a Tuesday class, and the next one is a Thursday. All right, and then you're expected to look at and do some of the homework assignments and blah, 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 and this and that. So I'll highlight the important parts of this. We are starting to talk about probabilities, and that's what today is all about, the probability of something happening, which was the start of our movie that I showed you to try to get you to, not be excited, I guess, about stats, but just know where stats started from. And it is from a probability situation. So an experiment is something that we collect data from. So we run an experiment, and we look at the outcomes of that experiment. The whole experiment is called the sample space. That is all the possible outcomes, and that's something we're going to write out today. A lot of your homework is write out the sample space. Then from that, what's the probability that, and then they ask you a specific question, and then the way it's worded. An event is, any collection of those outcomes, and it's can be a subset, and that's what they're talking about. What's the probability of this event? That's what we're actually saying. So from the sample space, what's the probability of a specific event occurring? So these are all terms that you could probably survive without me going over it so well, but that's fine. The first thing you want to write is what's highlighted here. You don't want to write all of this box out, but you do want to write, this is talking about theoretical probability first. This is not running an experiment, but thinking about an experiment. What is the probability that I flip heads on a coin? Everyone knows what that answer is. What is it? 50%. That's a theoretical idea. Okay? So what we have over here, which might be cool to write, is the whole idea of this. This is the sample space, the big rectangle. And what this is saying is the sample space is 8 possibilities. That's what those dots represent. And then they ask you a question, what's the probability of event A occurring, whatever that may be? Well, There's 3 outcomes for A. So the probability of event A occurring is 3 out of 8. And that's what this fraction represents that I will go back to. Probability, in the most basic sense, is the number of outcomes in your event you are thinking about, and we'll call that this, divided by the total possibilities of outcomes overall. And I don't want to but I should overwrite that yellow as well. Very simple, basic definition. I'll press pause as we write. Or they did a test. Yeah, I think this is what the movie was. The 2 heavy hitters that were created probability. Do you remember that? They were flipping coins. Okay, I think that's what it was. This is called the sample space. This is exactly what could happen if I flip 2 coins at the same time. And each coin is different. All right, let's call one a nickel and one a penny maybe. And the first one's the penny. The penny could be heads, the nickel could be heads, and that's it. Or the penny could be heads and the nickel could be tails, or vice versa. So those are 2 different events. Or they both could be tails. Tails, tails. So this is the sample space. There is a total of 4 possible outcomes. So then if you ask the question, what's the probability of getting heads and heads? That's only one of these possibilities out of the 4 total. So each one of these there's a 25% chance of happening. But then when you ask this question, and you better get used to this terminology, what's the probability of getting heads on the first coin? How many possibilities are there that occurs? In this list, how many have heads on the first coin? 2. So that probability quite simply is 2 out of 4, which is half. All right, probability 101. It's very simple. At least, at most, if I have at least $20 in my wallet, what does that mean I have in my wallet? $20 or more. What does that mean to have at most $50? $50 or less. English. So at least 1 head when I flip a coin, these 2 coins. How many possibilities are there? 3 out of 4. And that would be, that's it. I don't know why I put equal there. I could make it a decimal and a percent, and then we can make it a percent. But that's, up to you. Yeah. Oops. Experiment. So experimental probability, you do a study. You actually check if your coin, it was like they were talking about that your Uncle Larry, your not so trustworthy Uncle Larry has a loaded dice or a loaded coin, and it may be more landing on heads than tails, and he knows that. So you might want to conduct an experiment. Does this coin, is it a fair coin? So experimental probability, you actually flip it over and over and over again. And then how many flips you do are the number of trials in that experiment. And then we can think about, all right, let's test if this coin's legitimate. If I do 1,000 flips, then I should get roughly 500 heads, right around there. If I only got like 200 heads and 800 tails, that's probably good evidence that that coin is bogus. It's actually real good evidence. So that's why you would conduct an experiment. And then you don't have to write this down, but maybe the charts. Just put real quick, we're going to toss 2 coins 500 times and see what happens and see what we can say about this. Then write the chart. So here's the actual experiment. You flip the 2 coins 500 times and you collect the data. So now you can write this down if you wanted. Heads came up 137. Heads tails 115. Tail heads 108. Tails 140. And then I'll give you a chance to write. I'll pause the video for a second. Make a note to self that when you put these as a probability, what's the probability I get heads? Well, 137 out of the 500. These all add up to 100. All right, when you're talking about all the possibilities of a particular event. right, or a particular sample space. All the event probabilities add up to 100% if you cover all possible outcomes. All right? And by the way, I don't know if we can say, and that's what statistics are about, and that's what you're going to discover. But we can start analyzing this through statistics. Is this evidence that the coins are valid or not? Right? It seems pretty roughly okay. What should all of these numbers be? Like, what would the theoretical probability be? What should all of these be? Not that they should be, but what would they be in a theoretical sense? Who knows that answer? 125. Nice. All of them should be 125. I shouldn't say the word should, but the theoretical thing would be they should be roughly around 125, each one of these. Evenly split 4 ways. Okay, answer the question, student number 31. What's the experimental probability? What would I have to do with what I have up here? And I'll go offline and we'll get these answers and I'll describe them. Theoretical. Okay, so the difference between experimental and theoretical, you have to go off of the experiment in order to put the numbers in to calculate that scenario. Okay? I don't think I have anything else to say. I might have erased something down there. May I move on? Yes, Mr. Samuelith. Nice. Okay, all right. So now moving on. I'll give you a second to write this down. Or I'll just give you the quick thing. You have a jar, and it has 1 red, 1 green, 1 yellow, and 1 white marble. All right? And then we're going to calculate these off to the side. But the person I just picked, the first thing I'm going to have them do is write out the sample space. So I know how many possible different events could happen here. And by the way, I am going to continue to read this for you because it's important, some of the wording out of this. We are going to draw 2 marbles, one, then another. Excuse me. I've only been coughing since July. I'm fine. I'm not going to no doctor because they're a bunch of quacks. I don't trust any of them. Anyway, without replacing. So that means I'm going to pick the first marble, and then I'm going to put it in my pocket. Then I'm going to go back into the jar and pick a second marble. There's going to be a difference coming up. In some of them. Some of them you're going to pick, then you're going to throw it back in, shake it up, and then you're going to repick. And that's going to change your probabilities. All right. Press pause, and I'll pick on that student as far as getting the sample space. There's your sample space. And all I did with the students here was say that these are different events because they're making a point that you pick one, then you pick another one. So red-green is different than picking green-red. So what's the total sample space? 12 possibilities. Alrighty then. Where am I at? Student number 10. What's the probability that one of the marbles is red? By the way, what's the denominator of this probability? As said by over here, huh? Absolutely. One of them are red. What's the numerator? 1, 2, 3, 4, 5, 6. Boom shakalaka. And what does that end up being as a probability? 1/2 or 50% if you wanted to write it as a decimal. Moving along, the first marble is red or yellow. All right. So why don't you do it again? Because you're on fire right now. You got 1 in a row. Just because I don't feel like getting another student right now. So red or yellow. Oh, no, this is hard. What was that? Green? This is a stunning video right now. Is this R? Yeah. Red or yellow. Red. First marble is red or yellow. All right, you're good. Same thing. 6/12, which is 1/2. What's the probability, everybody, that both marbles are the same color? 0. Okay, so that's something that's going to happen in probability as well. Now, I'm running out of colors. I don't feel like erasing the situation. But this is also, and I'll go offline because I think you get it, what's going on here. So neither marble being blue is 100 or 1 or 100%. If you wanted to make it a percent, make sure you write the word percent though. All right, and make sure that that happens. Okay, so getting the idea of that. Okay, take a minute to look at this question. What does that say over here? What does that say? This is on the final exam. What? I don't know where I'm going. Oh, geez. I'm trying to hit stop and I'm losing. It's based off of an experiment. So that's all you can surmise from this. The doctor can say this because people of the past have exhibited this. So now we're trying to look into the future and say, and if there's a ton, like 1 million patients that this happened, and again, that's the law of large numbers, all right, then we could say future, we can make this conjecture, but that's the only thing that's true about what's listed up here. You know, it's based off of previous evidence, and then we can say, all right, because of previous things, we can make this conjecture that this is the case. Don't worry about writing all this down. I think you have 13 for your homework. I think you might like this, as opposed to what I did on the last one with the whoa. As how I did this last one, we could have done our sample space maybe a little bit better. All right, and this is what's nice about it. So go ahead and write this down. Okay, good for these people. They have nothing better to do than to toss a coin and then draw a marble from a jar containing purple, green, and yellow. Okay, what are my possibilities for a coin? What could I get? Heads or tails. And then what are my possibilities for drawing one marble? I could get what? Purple, green, or yellow. And you might like this. And this is that's all they're saying in these directions. You can create a sample space by doing this little vertical horizontal line kind of comparison. So what this means is I could get heads and then purple, or I could get tails and then purple. Or I could get heads and then green, and I could get tails and then green. And then heads, yellow, or tails, yellow. And that's my sample space in those little bars. That's a nice way of organizing the situation. Okay, then last but not least, wrong. I did have one more, and I think this is fine. A drop thumbtack will land with a point up or point down. The results for tossing the thumbtack 60 times are as follows. Point up 42, point down 18. I think everyone should be able to do this. The experimental probability that the thumbtack lands point up is 42 out of 60. So I'm not going to bore you with the details on this one. Hey, isn't 42 6 times 7? Right? So 6 goes into 42 7 times. 6 goes into 60 10 times. That's how you reduce a fraction. Right there, numeracy. And therefore pointing down to be 18 out of 60. So I do want to get to the end of this. And then 6 goes into 18 3 times. And then, of course, 60 10. And, of course, these add up to 1. Because those are all the possibilities. Okay, so based on this experimental probability, and by the way, 7/10 is 70%, and this is 30%. If you did the thumbtack 100 times the toss, how many times would you expect it to point up? I think everyone would know the answer to that. What would that be? What would that be? 70. Because it's based off of that experiment. Now we can make a conjecture about future thumbtack throws. All right? All right. I know this isn't exciting, but this is why I do this. Boom! Nice! I have a rule that if you get picked 5 times, that's it. You won't have to go a 6th time. But you're going again, ma'am. All right. Probability of A is getting a sum of 7. I've given them, oh, I should have put this for the movie, darn, but there's 36 possibilities, and I gave them a sheet that shows all those possibilities. Did you count how many times getting a 7? A sum of? It's actually a diagonal. And this is why a game is based off of this called craps. Anyone ever hear craps? It's based off of the rolling of a 7 because it is the most amount of occurrences of a particular sum. Okay? Then I'll leave it on. 8 dots. Now that gets a little bit harder, but it's not too bad. How many times do you see a sum of 8? Go ahead, someone say it out loud. 5. It's another diagonal, a little shorter and a little smaller than the other one. That doesn't reduce. We could turn that into a percentage, and that would be fine. What does at least 4 dots mean? At least 4. That means 4 or what? All right, now I wish I had the picture of my cards, but look at as I motion up here. At least 4, that is this event right here. And then all the rest, right? Because at least 4 means 4 or more. What's the opposite of at least 4? What's the opposite of at least 4? How many do not make a sum of 4? How many possibilities? 3, right? So what's the probability you do get it? What's the opposite of 3? Not the opposite of 3, but as far as how many there are. 33. So sometimes it's and that's why I asked you before, did you think about the complement of the event? Like, do the opposite because it's smaller and then do 1 minus that. All right, and that definitely reduces to 11/12ths, right? 3 goes into both, and then you could turn it into a percent. So hang on to these to answer those questions. I wish online I had that picture. Maybe I'll do it real quick. I'm done. Here's those die I was talking about. All right, I can't really get it up in that situation, but that shows all the possibilities of rolling 2 different die, what different sums could come up. So figure I'd finish the movie with that.